We're going to talk a little about symmetries today, and the two symmetries we're going to discuss are point symmetries and line symmetries. So as you can see in this sentence here, the line is going to be an axis of symmetry if it is a perpendicular bisector of any 2 points on the graph. So if I look here at a point and here at a point and say this is my line of symmetry, that line is perpendicular bisector between those 2 points. Okay? If I'm talking about a point of symmetry, where this big point right here is the point of symmetry between 2 points on this curve, then if I take a point right here and say that's my point of symmetry, then that point in the center is going to be actually the midpoint of the segment connecting those 2 points. So point symmetry and line symmetry. We're going to take a look at some special types of these. First, we'll take a look at line symmetries. And the first line symmetry we're going to look at is what we call x-axis symmetry. Now, if the x-axis, which is this horizontal line here, is the line of symmetry for a graph, then you'll notice if I pick any point on that graph, let's call this point right here xy, we'll call it point P, and say, all right, I want the x-axis to be my axis of symmetry, then I should be able to flip this point over this line and end up at a new point that's on the function. And you notice that on the other side of that line, there's a curve that is its, if you will, reflection. All right? And that point is what we say mapped onto this point right over here. And we're going to call this point P prime, and if you remember from geometry, that's called the image point. So you'll notice once again that the line of symmetry is perpendicular, and it's also a bisector of the segment joining the points in question. Now, if we look at y-axis symmetry, this right here, we notice that if we pick a point, we're going to call this our point, let's call it P, and that's some xy point. Then when I reflect over that line, the y-axis, I map onto another point over here. And you'll notice the coordinates of the image point. So x now goes to negative x, but it's still just as high, so y is still y. When we go back to the x-axis, again, you notice it's still just as far out, but I've gone from a y coordinate to the opposite of y. So let's look at a couple of more line symmetries. We've got a y equals x symmetry, and here I've picked this point P, call that xy. And if I use this as my line of symmetry and draw a segment connecting those 2 points, then the line of symmetry y equals x is perpendicular and it bisects the other 2 points. Now you notice the relationship between these 2 points. If this is some xy point, in other words, over 2 and up 6, you'll see that this new point looks to be roughly 6 away, but only up 2 high. So really what's happened is the y value and the x value have switched. And that's what's unique about y equals x symmetry. If we look at the line y equals negative x, and I pick some random point, we're going to call it P, right here, and give it the value of xy. And again, I make another point after flipping it over. That new point, its image point, is going to be over here. I notice once again that the line y equals negative x is perpendicular and it bisects the segment connecting those 2 points. You'll notice that if this were just a little bit away, it's a lot up. Well, now take a look over here. This is a lot away, but a little down. Okay? And notice, a little bit away to the right, a lot of it away to the left. All right? A lot up, a little down. So you'll notice the relationship here, if I start with an xy point and do y equals negative x symmetry, my new relationship is the opposite of y and x. Those are the 4 line symmetries we're going to look at. We're also going to look at origin symmetry. Now, the origin is basically just the point 0, 0. So here's my origin. Whoops. So if I draw my origin once again here, I notice that if I connect the dots of xy for the point and the image, that this segment is bisected by this point. And you'll notice the relationship is this is a little, like, let's say 1 over and 2 up. Well, this is 1 in the negative direction and 2 down. So the relationship between the two is xy and negative xy. This is a point symmetry, the origin. All the others were line symmetries. We're going to outline some of these symmetries. First of all, x-axis symmetry. If the point is xy, it flips over to x and negative y. And you can see that by drawing it. To test if I have y-axis symmetry, then if I have xy for my point, negative xy is also going to be on the graph. So basically, we want to get the same result by plugging negative x in that you would if you were plugging x in. If we have symmetry of y equals x, we know that if we start with an xy point and flip over the line y equals x, we end up with the xy point moving to a yx point. In other words, if I interchange both the x and the y, I get the same result. And finally, in our line tests, if I'm looking for, I actually didn't include y equals negative x, then we know that xy would go to negative y, negative x. That's included on the previous page. If we want to look at the origin, then we notice if we have an xy, then negative xy is also going to be on the graph. We're going to go through some proofs. First of all, we want to show we have origin symmetry. And we don't even have to know what these graphs look like to test for origin symmetry. Now, what I've done is I've included the test we're going to use for this specific example. All right? I want to show that y equals negative x cubed plus 5x is origin symmetric. And it's a cubic function. If you remember from Algebra 2, cubic functions look something like this-ish. But we don't have to graph it. We're not going to. We're just going to apply this test where xy represents our point and negative y, negative x represents our image. All right? So this equation represents basically x being x and y being y. Now, if I want to show this is origin symmetric, I have to substitute negative x for x in my equation and negative y for y in my equation and show that I get the same result. So I'm going to do that. I'm going to say negative y, because I'm substituting that for y, equals negative 3x, which we're substituting with negative x, raised to the third power, plus 5 times negative x. So again, I've substituted the opposite of x for x and the opposite of y for y. I have to show that this new equation is the same as the original. Well, grind a little bit out. Negative x quantity cubed goes to a negative x cubed. But multiplied by negative 3 and we get a positive 3x cubed. So far, these aren't the same because I have a negative 3x cubed here and a positive 3x cubed here. Minus 5x. Now, I notice this is a negative and this is a positive. So far, it's not looking good. I'm just going to divide both sides by a negative 1 so I get y equals. So at least I know the left side is going to look the same. I get negative 3x cubed plus 5x. Now you'll notice in this specific example that there is a difference. In my original, I have y and I have y. I have negative 3x cubed, negative 3x cubed. So far, so good. And notice what's happened in the end. My negative 5x has gone to a positive 5x. So indeed, this equation is the same as the original equation after substituting the opposite of x for x, the opposite of y for y. Therefore, yes, this is origin symmetric. I've proved it. I want to show that y equals x to the 6 is also origin symmetric. So again, what I'm going to do is I'm going to substitute a negative y for y. And I'm going to substitute a negative x for x. Now if I take negative x, take that to the 6th power, I get x to the 6th. Negative y is just negative y. Divide both sides by a negative 1. So I have y equals negative x to the 6th. In this example, while I have y is equivalent to y, negative x to the 6th is not equivalent to x to the 6th. Those aren't equal. So therefore, this is not origin symmetric. Let's move on. Again, I want to show which line symmetry exists. We've got 4 lines that we're talking about. We have x-axis symmetry. If you remember, x-axis means that if I am here, flip over, then I'm here. So in other words, my x-axis symmetry test is going to show that if I have xy and I flip it over, I get x negative y. So I'm going to substitute x for x and the opposite of y for y. Let's do that. X squared plus the opposite of y for y is equal to 8. We notice right away that I have x squared plus negative y is 8. In my original, I had x squared plus y. These are not the same, clearly. So this is not x-axis. We do y-axis. Which says that if here's my y-axis and I put a point to the right, flips over on a point to the left, which means I'm trying to show that if I have some xy point, then the point negative xy is on the graph. So I'm going to substitute the opposite of x for x and y for y. Do that in this initial equation again. So the opposite of x for x gives me x, the negative type, square that, substitute the y for the y, get 8. Now notice, the opposite of x squared is x squared plus y is equal to 8. This equation is the same as my initial equation. So yes, y-axis symmetry. If I go y equals x, again, sketch of the line. There's my line of symmetry. Put a point here. Flips over that line to a point here. So I'm going xy maps over to yx. So now I'm going to switch the x and the y values in my original equation and hope that I get the same outcome. X squared now becomes y squared. Y becomes x. And clearly, you can see that these will never be the same, because here I have x equals 8 minus y squared. And if I was to isolate x in the original equation, I'd have x squared equals 8 minus y, getting x by itself. I'd have to actually square root something, right? These two terms in no way look alike, so no. Right? I do not have y equals x symmetry. We really, I mean, to be fair, we'd have to do one more test, which is the test of y equals negative x. To do that, we'd have to show that xy, looking at the graph once again, here's my line of symmetry. I have a point here, it maps to a point here. So therefore, if I have xy, that's going to map to negative y, negative x. Test it in the original equation. So x squared becomes the opposite of y squared. Plus, what was y now becomes the opposite of x. And that's supposed to equal 8. Opposite of y squared is just y squared. Opposite of x is just minus x. That's equal to 8. We're trying to get an x squared value in our answer, and there's no way that's going to happen, because in order to get y by itself, I'd have to square root it, thus x never becomes squared. So no, I've shown that that is not symmetric. So I can do one more example. Let's try another line symmetry in this case. And if you remember, which I'm not sure you do, from Algebra 2, this is the equation of a circle. And we know circles have lots of different symmetries about them. We just have to know if it's one of the lines that we have. So again, if I want to test x-axis symmetry, I need to show that xy is the same as x and negative y. So I start plugging in. X is still x. That's the same exact first part of the equation as I had before. But y now becomes negative y. So you'll notice x minus 2 squared has not changed. It's the same exact as the original. The opposite of y squared is just y squared. 1 doesn't change. So you'll notice these are the same two equations, which we wanted. So yes, that is x-axis symmetry. I'm going to just do one more for kicks and then let you do the last two on your own if you choose. So if I want to say, let's go y-axis symmetry. In y-axis symmetry, I have to show if I have an xy, then that's going to map over to the opposite of x and y. So in this case, the y's are going to stay the same, but the x's are going to switch. So what I have really now is I have negative x minus 2 quantity squared plus y squared equals 1. All I really need to show is that this negative x minus 2 squared is different than x minus 2 squared. Well, I'm going to do that by expanding. This goes to x squared. I multiply this by itself. Negative x times negative 2 is positive 2. And then I do it again because I'm foiling. Negative 2 and negative 2 is positive 4. Plus y squared. So now, if you will, I'm going to take and expand x minus 2 quantity squared. If I do that, I get x squared minus 4x plus 4 plus y squared would equal 1. So where's the big difference? Y squared is the same. 4 is the same. That's positive 2x and positive 2x, which is positive 4x. This is negative 4x, so no. That's not y-axis symmetry. And again, I'll let you do the last one on your own. Now, we're going to take a look at a graph. And I want to redraw this graph so it's origin symmetric. We've talked a little bit about origin symmetry. And we know that if it's origin symmetric, here's an xy axis. And I put a point up here, and I flip it over the origin, which is here. I come down, and that's my symmetry point. In other words, my x and y moves to the opposite of x and the opposite of y. So if I want to redraw this picture so that it has origin symmetry, I'm going to find out the x's and y's at some critical points on this graph, and then I'm going to make the opposites of those points, and then I'm going to check to see that my new picture is symmetric about the origin. So I look at where this point is right here. And I count over 1, 2, 3, 4, 5, 6, and up 1. So instead of over 6 and up 1, I'm going to go back 6 and down 1. 1, 2, 3, 4, 5, 6, down 1, and I'm going to put a dot there. Then I'm going to take a look at this point, and I'm going to go over 3 and up 4. So now I'm going to go back 3 and down 4. Back 3, down 1, 2, 3, 4. And I'm going to put a dot right there. Finally, I want to take a look at this point. I'm going to go back 1, 2, 3, 4, 5, up 2. So now I'm going to do the opposite of negative 5, which is positive 5, and the opposite of up 2, which is down 2. So I'm going to go over positive 5, 1, 2, 3, 4, 5, and down 2. Put a dot there. Whoa, hate it when it does that. And then I'm going to take and connect the dots. When I connect the dots, it won't be super pretty. It'll be close. You'll see that I have a new, somewhat triangular figure. And if I take and call this blue point right here my origin, then I would need to show that the segment from this point through the origin over to that point is bisected by the origin. And it is, which is great. I need to show that a segment drawn from that vertex down to this vertex is bisected by the origin. And it is. So this green figure is the new graph that is origin symmetric with the graph in black. That's how you go about doing that. So we're pretty much done. You're going to answer these questions. Most of them are multiple choice because they deal with graphs, and it's hard to answer the forms with graphs. So here are the first two. I'll let you look at those for a sec. And then I'm going to scroll down to get the third one and the fourth one today. So I'd like you to take and do those. You don't have to show any proofs or anything. You will tomorrow in class. Just answer the questions. Remember, we only have 1 point symmetry, which is origin at this point. And we have 4 line symmetries, x-axis, y-axis, y equals x, and y equals negative x. See you tomorrow.